Welcome to the Avid Technology Podcast with me, Ryan Morn, from wherever in the world you might be listening. Thanks very much for taking the time out to listen to us today. In this podcast, we're going to talk about battery technology, specifically the cells. We've been promising to do this for a while now, and we get lots and lots of questions about batteries, because really battery technology is one of the key enablers in vehicle electrification. Reducing costs and improving performance of batteries is what's allowing us to do so much more things now with electrified vehicle powertrain. So in this podcast, we're going to talk about the current state of the art and the future trends in battery cells for electric vehicles, but we're going to start with some of the basics. So basically, in a battery pack, there's several key subsystems. So it's not just all about the cell. We do have the actual battery cell, of which there are many in an electric vehicle battery. There's several different kinds of cell. But basically, if in your head you can picture a big version of the AAA battery in your TV remote control, and you'll be pretty much picturing the 18650 cylindrical cell in the Tesla Model S. So called because it's 18 millimeters in diameter and 65 millimeters long. The new cells in the Model 3, the 21700s, guess what, are 21 mil in diameter and 70 millimeters long. There's also some other kinds of cells called pouch cells and prismatic cells, but more on that later. The cells in a battery pack are arranged into strings inside the battery, and a combination of these in series and parallel gives us the pack voltage from the amount of cells we have in series. So if we had 100 4.2 volt cells in series, we'd have a 420 volt battery pack. And then in parallel, we get the capacity of the pack. So we add strings of cells in parallel to each other to increase the capacity once we've got the pack to the voltage that we need. So you might often see an electric vehicle battery being described as something like a 96S 2P. And what that means is 96 cells in series and 2 strings of 96 in parallel. So that's a lot of cells, and actually in that case that wouldn't still be a particularly large battery pack. But that sort of number S, number P denotes the number of cells you have in series and the number in parallel. So there are a lot of cells in a battery pack, but that is not all there is to a battery pack. Obviously then, in addition to the cells, we've got quite a complicated electrical system, an electrical distribution system, so we can get the electricity in and out of those cells. So there's lots of buzz bars and interconnections. We've also typically got a cooling system inside the battery pack, and different batteries have different level of complexity of the cooling system. There's all the mechanical support for cells themselves to stop them from floating around inside the battery. Obviously, you don't want that. They have to be securely held in position and typically also held against the thermal management system. And then you find a very complex system of electronics called the battery management system. And this is there to monitor the cells for their condition, to make sure nothing bad happens to them, and also for their state of charge. One of the things with particularly with a lithium cell, is it's quite hard to actually tell how full it is, because they've got quite a flat charge-discharge curve. So the difference in the voltage of the cell, a lithium cell, between its fully charged and fully discharged is not very big, and it's very flat in a big portion of that charge-discharge portion. So we have to very, very carefully monitor the cells to know how much charge we've actually got inside the battery pack. So all of that kind of safety controls and condition management is done through what's called a BMS, a battery management system, and that'll be quite a complex system of electronics inside the pack. So as I mentioned earlier, in this podcast, we're not going to talk about all of those things. We're just going to concentrate on the cells. In general, I mean, it's fair to say battery development is focused on 3 key areas. Reducing cost is really important. Battery is the biggest cost item in your electric vehicle. And improving energy density, that's the second biggie. So basically the amount of electrical charge that we can hold in the battery per unit of volume or kilogram of weight, that's really, really important. And then, of course, the final thing is improving the stability and the safety of those batteries. So at the minute, the batteries are pretty safe, but you've got to really look after them to make sure that nothing happens to them. And people are trying all the time to make it so that those are more robust. So basically, you can hammer nails through them and nothing will happen. In this episode, I've said a couple of times we're going to do the battery cells themselves. It's a key component of the battery pack. But then the cell itself is a structure. So there are several key components in a battery cell. We've got an anode, a cathode, a separator material, and an electrolyte. So the anode basically is an electrode inside the cell. The metal at the anode is being oxidized to release electrons as the cell is being discharged. And normally in a battery pack, the anode is the negative terminal of the cell as the cell is being discharged. And this would typically be copper foil coated with graphite. So if you chopped open a lithium cell, you'll find some sheets of material in there, and one of them will be a black colour. This will be the anode, typically. The next part is the cathode. So the cathode is the other electrode in the battery cell, and this is where reduction is taking place during the discharge cycle, and electrons are moving into the cathode. So for lithium-ion cells, this would be the positive terminal on the cell, and it's also where we have the really interesting multi-metal and metal oxide compounds, the nickel, the manganese, the cobalt, all that interesting stuff mixed up with lithium. So already you might be a little bit confused, and there's one key point here that I just want to make. So electrons actually flow in the opposite direction to how we describe conventional current flow. So electrons are negatively charged, so they flow from the negative terminal of the battery into the positive terminal, whereas we typically describe current flow as being from the positive terminal to the negative terminal. But actually that's not technically strictly correct, and that's basically because electricity was discovered before people knew what electrons were and how they moved around, and unfortunately the assumptions were made about how the electrons were moving weren't quite right, basically. And now we know that, but all of the rules and the laws were kind of written for going the other way, so we just have to deal with the slightly confusing situation that actually electrons go the opposite direction to how we describe current flow. So anyway, that aside, for lithium cells, they're rechargeable, and actually what you also have is that the electron flow changes direction depending on whether you're charging or discharging the cell. And so if you want to be sort of technically correct, the anode and cathode switch around. So whilst we would always describe the negative side as being the anode and the positive side as being the cathode of the cell, actually technically during charge and discharge, they reverse roles and switch around. So next, as well as the anode and cathode, we have a really important piece of material called the separator. So the separator is a really thin sheet of permeable polymer that keeps the anode and cathode separated, so it does what it says on the tin, and that's to prevent an internal short circuit in the cell. So we want to insulate the anode from the cathode, so we're not short-circuiting them out, but we still need to allow ion migration inside the cell through the electrolyte. So the separator is permeable, and it holds the electrolyte in pores in it. So finally then you have the electrolyte. The electrolyte is a liquid that allows the ions to move around between the anode and cathode, and the electrolyte will typically consist of a lithium salt dissolved in a volatile solvent. Now the solvent is very flammable that is used, and that's one of the problems with current lithium cells, that basically every cell is filled with very flammable solvent. So if you have an issue with the cell where it overheats, basically that solvent goes through a process of off gases. So you might have seen pictures of pouch cells that are kind of all bulged and funny looking, and that's because the solvent started to evaporate. Very easy then for that solvent to catch fire and result in a fire, which is a major issue, and people are always looking to control that and prevent it from happening. But it's a really important element in a lithium battery is the electrolyte. So when we're building the battery, there's the cell is structured by combining thin sheets of these materials together. So in a cylindrical cell, as Tesla use, they're tightly wound into a spiral and they're packed inside a metal can. In a pouch cell, such as the ones used in the Leaf and the Kona and the I-Pace, the sheets are stacked and then they're put into a polymeric pouch, which is then filled with the electrolyte. And then finally, the third type of cell, the prismatic, which is essentially a hard box with the anode, cathode, and separator material folded into it. This does allow a bigger volume of material, and it's a bit easier to handle than a pouch or a cylindrical, but it's not very volumetrically efficient. Metal case prismatics are currently used by BMW, and they're used in some other vehicles as well. And they're not bad. They offer a good level of protection, and they're easier to handle. But really, the two kind of dominant cell types are becoming the cylindricals and the pouch cells. There are different camps of people. Some people prefer the pouches, some people prefer the cylindricals. I can see the advantages and disadvantages to each. With a cylindrical, the manufacturing process has got fewer steps, but there's extra packaging. Thermal management can be an issue with cylindricals because inherently you get temperature gradients across the layers, which can accelerate dendrite growth, and it's difficult to cool them. With a pouch cell, they're easy to cool, but they're floppy. They need mechanical support. The manufacturing process is much, much harder because you've got to very carefully align the very thin layers of material one on top of the other and hold it very carefully and build the pouch. And it's very difficult to make pouch cells. Basically, there's a lot of processing technology involved in that. But once you've got that cracked, it's fine. With all kinds of cells, it doesn't matter what the structure is, there's a secondary process. So once the cell's actually been assembled, it then goes into a post-assembly conditioning process where it's been filled with electrolyte, and then it undergoes very careful conditioning to ensure that we've got a really good distribution through the cell structure of electrolyte, and then the cell activation process. And basically in the activation process, we very gently charge the cell, and we force the electrolyte to decompose into a very, very thin layer on the cathode, and that's called the solid electrolyte interphase layer, or SEI. And this actually can take weeks. It's a huge part in the battery manufacturing process, going through this kind of bringing the cell to life and then carefully aging it and getting it into a condition where it's stable and it can be used. So reducing and optimizing that part of the process is a massive opportunity to get cost out of battery cells. So the next kind of big area that people are concentrating on in terms of trying to get higher energy densities is through using thinner and thinner material. And basically, by thinning down the material for the anode and the cathode and the separator, it means you can get more individual layers of that material inside a given volume. And you've got more efficient use of that material. You've got less sort of dead material sitting in the center of each volume of it. But very thin sheets are incredibly hard to deal with from a manufacturing process point of view. And they also struggle in terms of dealing with high electrical current flows. So really, this has kind of created at the moment two different categories of battery cell. We've got energy cells that are made from very, very thin materials and cell chemistries that are focused on energy density, but really at the expense of charge and discharge rates for the cells. And then we have power cells, which are typically used in hybrid cars or very high-performance vehicles, which use a thicker material to allow a higher charge and discharge rate, but typically at the expense of absolute energy density. What you would see is a normal energy cell, so the kind of cells we're putting into things like the Leaf and the Kona, might be able to charge and discharge at a rate of 3C. And what that means, the C rating of the cell is quite important. So if we had a 100 kilowatt hour battery pack, and it was rated at 3C, we'd be able to push 300 kilowatts in and out of it. But a high power cell, we might be able to run at 10 to 15C. So that 100 kilowatt hour power battery pack, we'd be able to push a megawatt or more in and out of it of power. And that's really important when you think about the power of the electric motors that are actually on the vehicle. And the reason it's been so important for hybrids is you have a relatively small battery pack in a hybrid car to the power of the electrical motor that you're using. So you need a much higher C rate. So thinner materials are a really big thing, and you've got the conventional cell construction method. So basically just thinning down the foils and the film materials that are used to improve the construction. So no kind of massive changes, basically incremental improvement into better, more thinner films. One of the big issues with lithium batteries is something called dendrite growth. So basically dendrites look like little branches of trees, and they grow out of the cathode in a lithium cell. And they grow when the cell is charged and discharged, and if it exceeds certain temperature ranges, they grow more they grow more vigorously. And dendrites can puncture the separator material, and they can actually cause a short circuit inside the battery pack, and obviously that could be really bad. So managing dendrite growth is really, really important, and that comes down to how we manage the condition of the battery, how we manage the charge in the battery, the charge discharge rates, and how we manage the temperature of the battery. But it's a really, really important area. And one of the issues is if we have very thin materials and very thin separators, it becomes easier for the dendrite to basically puncture the separator. So if with a thick separator in there, we've got a bit more tolerance in terms of being able to tolerate some dendrite growth inside the pack before there's a risk that we're going to do any damage. But as we thin the materials out, it becomes more and more critical. So basically, one of the other things that we see is very high energy density batteries with very thin materials need to be very carefully thermally managed. And that's what you would see in terms of the trend in vehicles, where we've gone to very complex now active thermal management for the battery packs. And that's as a result of thinner materials and trying to manage dendrite growth, make sure that's not a problem, and control the battery pack. So then what's coming next? So basically beyond radical chemistry, which are, there are things happening with radical chemistry innovations, but they're basically a long way away from the market. So there's people looking at different material combinations at quite a fundamental level, so moving away from lithium altogether. And there are things on the horizon there which might present some significant leaps forward, but that would come under the category for me of a radical chemistry innovation. The next thing we've got is sort of incremental improvements in the battery. I've talked already about thinning out the films, playing around with the chemistry at the cathode, doing different kind of doping, using nanoparticles of some clever materials to improve the performance. There's all sorts of basically fairly moderate incremental improvements happening to the existing kind of battery structures, and there's a lot of activity around that. There is one thing, and we get asked about this all the time, so the big thing which people are kind of hanging out as being the next big thing in batteries is solid-state batteries. So a solid-state battery, what is happening there is, rather than having a liquid electrolyte in the battery, we get rid of the liquid electrolyte and we've got a solid material. So essentially the electrolyte and the separator are replaced by a solid material that's a very carefully constructed material that can allow ions to move through it, but is electrically insulating and typically more thermally conductive than the materials that are currently used. So solid-state batteries are getting an awful lot of attention. The difficulty with them is they're very hard to make. The purest ceramic solid-state materials, the processing isn't there yet in terms of high-volume production. And then they also have issues with thermal management. So again, you've got very, very thinly deposited layers, actually to the extent where they're not such a problem with thermal effects, but then they're bonded mechanically together. So in a conventional cell, basically everything is floating around in the electrolyte. So if we have expansion and contraction of the anode and cathode at a differential rate because of heating and cooling, it doesn't really matter. With a solid-state cell, it's really important. The expansion and contraction of the anode and cathode materials, we can cause stress at the interfaces between the anode, the cathode, and the electrolyte separator, ceramic, and managing all of that is really difficult, and there's a lot of work going into that to improve the performance of those solid states and make them so they're reliable and durable to the point at which they're suitable for use into automotive. And actually what we can say is that we're starting to hear rumbles of fairly near to market launches coming for these solid state cells. So we had Mercedes making some announcements when they launched the Citaro electric bus recently about solid states. We've had Fisker talking about solid state cells in terms of being in the market within the next 2 or 3 years. So that's excellent. That's going to represent a huge step forwards. Solid state cells have got the potential to be 3 to 4 times more energy dense than a conventional cell, and they've also got the potential to be much, much safer. So if we get rid of that solvent from the electrolyte altogether, then we can improve the safety massively. There's still some challenges. The thermal management of solid states is going to be very tricky. The C rating of solid state is an issue because the very, very thin materials then can't deal with very high current flows particularly well. But the potential to use them in battery systems combined with other things is excellent. So we're seeing lots of really interesting things happen around cell development with solid state at the moment. There's a kind of a quasi solid state battery where basically we've got instead of a liquid electrolyte, we've got a gel or a polymer. Now the sort of purists would say it's not a true solid state battery. These batteries are kind of available for different applications now. Again, there's some issues with those in terms of making them suitable for automotive applications, and I think the main kind of priorities recently have been on all ceramic types. The polymer is not being particularly favoured. But, we'll see what happens. It's clear, though, there's lots of things going on at the moment with battery cell technology, and there's really some huge improvements coming, not without challenges, and not least certainly the improvements to date in terms of energy density have all brought around thermal management and current management challenges due to the much, much thinner materials being used. The solid state is going to be great. Getting rid of those electrolytes is going to be fantastic, so really keep an eye on that. So that's all for this episode. Thank you very much for your time. I've run a little bit over what I was expecting to do. Thanks for listening. We really appreciate it. We'll pick up on battery thermal management and battery management electronics, BMS systems in future episodes, so we'll be coming back to this. We'll also be coming back to cells down the line. There's some really exciting things coming, and we get to a point where they get into the public domain and people can talk about them. We will pick up on cell technology again. If you've got any questions, please feel free to send them in. We've had a really good response with people asking us questions, which is then giving us ideas for what to do for future episodes for the podcast. If you've enjoyed this, please leave us a rating or hit like, depending on which platform you're listening to us on. And of course, don't forget to subscribe to the channel. So that's all for today. Thanks very much for listening, and I look forward to talking to you soon.